This conference will now be recorded.
Hello everyone. In last class we have finished with that is the physical properties of alkali metals. Alkali metal means group 1 metals. So in S block elements, that is the chapter, we have two groups, group 1 and group 2. So group 1 we have started in the last class, which is alkali metals. All the alkali metals are present in the group 1. Now up to physical properties we have finished. Today we will focus on chemical properties of these elements, that is alkali metals. But first we'll solve some problem, whatever we have completed in the last class. Based on that we will solve some problem. Here we have assertion reason type of problem, and there will be two statements. In the light of the above statements, we have to choose the most appropriate answer from the options given below. Now the first statement, assertion, it is saying that the alkali metals and their salts impart characteristic color to reducing flame. Now it is true that alkali metals, they impart color in flame, but is it reducing flame or it is oxidizing flame? That is another question. Now it is not reducing flame, it is basically oxidizing flame. So that is why this statement is not true. And what about the second statement? It is saying that alkali metals can be detected using flame test. Now that is true, because when we do flame test, there is specific color for each alkali metals. So from the color you will be able to understand which alkali metal salts are actually present. Okay, so the first statement, that is not correct, but the second one is correct. But what is this reducing flame or oxidizing flame? See, when we have flame, that this is the flame that you are seeing here, this is blue color, right? Now when it is in blue color, that means it is oxidizing flame. And here the platinum wire that is used, platinum wire, and in the tip of the platinum wire there is basically the salt present. Now it may be lithium plus, it may be Na plus salt, it may be K plus salt, anything. Now from this color, which is bright yellow, it seems as if it is sodium, but whatever it is, that is not important. Important point is whether it is reducing flame or whether it is oxidizing flame. So oxidizing flame is always used for flame test because it has higher temperature compared to this reducing flame. Now how you will differentiate when you will do the test, that you can understand from the color. So when it is oxidizing flame, it is basically blue color, but when it is reducing flame, it is basically yellow color. Fine. And in this way, from the flame, that is, I'm talking about this part, that is the flame, whether it is reducing flame or oxidizing flame, that first you have to confirm. Once you understood, and here by proper controlling of the air, we can correct it. That is, we can change the reducing flame to oxidizing flame. That depends on the burner mechanism, but we can do so. But remember, ultimately we need this type of flame which is blue in color, because that is actually the oxidizing flame with very high temperature, and that is used for this flame test. So the statement which is given in assertion, that is actually partially correct statement. It is not fully correct. This part is not correct. So that is why we cannot say as a whole this statement is correct. So option 3 is saying that A is not correct, but R is correct. So this option we have to choose. Okay. For alkali metals, which of the following trends incorrect? We have total 4 trends. The 4 trends, first one it is based on hydration energy, second one ionization enthalpy, third one density, and the fourth one atomic size. And here we have total 4 elements: lithium, sodium, potassium, and rubidium. So all these are from group 1, that is alkali metals. Now these properties, that is physical property and atomic properties, that we have finished in the last class. And remember, we have seen this type of table in the last class, which will help you to answer all these questions, which is based on not just physical property but also some atomic properties such as ionization enthalpy, okay, or electronegativity. So here if we see hydration enthalpy, it is saying that the order is such. Now look at the hydration enthalpy. Hydration enthalpy, whenever you will solve question, that is whether it has high value or low value, you have to just focus on this magnitude. Don't consider with the negative sign. Negative sign is there because it is energy liberated. That is why the negative sign. But if you simply focus on the numerical value, it is 506, then 406, then 330. So basically it is gradually decreasing as you are moving from lithium to sodium, that is as you are moving down. So the value will decrease, and that is also given in the option 1. So this is basically true. It is not incorrect. We have to find the incorrect one. That is the correct option. Then the second one is ionization enthalpy related. Now this is very easy to understand, even you don't need this table, because ionization enthalpy, as down the group extra shells are added, and that effect is predominating over the other effect that we have also discussed in detail in the last class. So as extra shells are added, the removal of outermost electron, it becomes easier as you are moving down the group. So that is why it will be most difficult for lithium. Then when you are moving to sodium, potassium, rubidium, gradually the process will be easier. Now the process will be easier means what? You have to provide very less energy. So this is also true. Now come to the density. Density, there is not any smooth trend. See, from lithium, it is gradually increasing, but there is the discrepancy between sodium and potassium. It is increasing down the group, but here suddenly you can see this discrepancy. Sodium is more dense compared to potassium, but here it is mentioned as after lithium, it is sodium, and after sodium it is potassium, but potassium is basically less than sodium. So that is why this is actually false, and that is why this is the correct step. And atomic size, it is very easy to understand. Down the group it increases, so RB max, then gradually it is shorter the size. So option 3, density, this is incorrect, and we have to find the incorrect one. Next question, alkali metal from the following, that is RbNaKCS, with least melting point. So here we also have melting point, and as you can see, there is smooth decrease down the group. So this one will be the correct answer. But that is fine. But what if we want to know what is the actual reason behind it, why it is decreasing down the group? Then the reason is, in group 1, as you are moving down the group, the distance of electron, that is the valence electron from the nucleus, from the center, that distance is increasing. And as a result, this valence electron, which is basically involved in metallic bond formation. What is metallic bond? If you want to know in detail, you have to check the previous class. Okay. So only the valence electrons are involved here, and if these valence electrons, they are far from the attraction of nucleus, they can move very easily. That means this type of bonding will not be very strong. It is very weak, and you can melt it easily. So this is the actual explanation. So correct answer is cesium. Now we will start, after discussion of these problems, the chemical properties. Now chemical properties, some that is points we have already done in the last class, but still we'll start it freshly. Now some information before actually when we will see the equations, how it is reacting with different elements. Before starting that, first of all you have to know that they are very reactive. That means there will be versatile type of reactions you can expect, that is they are reacting with different types of elements. So why their reactivity? They exhibit high reactivity because their ionization energy is very low because of the large size. If you simply consider the periodic table, that is a particular period, if you consider group 1 is the leftmost, and in the leftmost, if we consider the periodic table chapter, there we have seen that in a particular period, when we move from left hand side to right hand side, horizontally size decreases. Now size decreases means you cannot remove the outermost electron so easily, but if we do, we can remove this electron very easily. That means ionization energy is very low because of this large size. Then obviously it can take part in reaction very easily. Simply take any metal, that is group 1 metal. If it can lose electron very easily, it can form plus, and that lost electron, it can react now with other elements. The reactivity of alkali metals, it is high, that is fine, but what will be the trend? The general trend is, as you are moving down the group, that is lithium to cesium, obviously the reactivity will be high, and the reason is overall in general their ionization energy compared to other elements in the periodic table, it is less. But if you simply compare among themselves, that is just you are comparing the ionization energy of all the alkali metals, then down the group it decreases because of this extra distance of electron from the nucleus. So since ionization energy is decreasing down the group, so reactivity, which is directly related to ionization energy, that will also increase down the group. They are very electropositive because see, they are metal, the most electropositive metal, even though it is true that there are different types of metal in the whole periodic table, but these alkali metals, they are the most electropositive, highest electropositive character compared to other metals. They are specifically reactive towards highly electronegative elements such as oxygen and halogen. In general, I am writing X, that is fluorine, chlorine, bromine. Because oxygen and halogens, they are from group 16 and group 17 in the left hand side of the periodic table, and they are the most non-metallic, they are having the most non-metallic property. And these alkali metals, they are very electropositive. So the reaction, both these elements are very reactive. So obviously when they are together, the reaction will be very vigorous. First we'll see the reaction with air. Now when I'm talking about air, there is both oxygen present as well as nitrogen is present. So first we'll see how these alkali metals, they react with oxygen, which is present in air. All the alkali metals, when they are exposed to air, which means basically they are exposed to oxygen, there is rapid tarnish because of formation of oxide. So they form oxide compound on their surface, and that is the reason now the metallic luster is lost because the metal is no longer present as metal, and it may rapidly happens in the surface area, because in the surface area the atoms are mostly exposed to the air, that is oxygen. Okay, now these oxides, it is not having any general formula. Depending on which alkali metal you are doing the reaction, depending on that there are different types of oxides. So we will see one by one. Lithium, which is the first first element, it forms only monooxide. Now monooxide is simply O2 negative charge. The next element, which is sodium, it forms both monooxide and peroxide, though this is most prevalent. Monoxide, even if it is formed, that is not so significant. Peroxide is most important. And what is peroxide? Peroxide is 2 oxygen atom with 2 negative charge, or you can write it like this. Okay, it is easier to understand, but you can also write it as O2 2 negative. And after sodium, the rest of the elements, that is potassium, rubidium, they form superoxide. Now what is superoxide? Superoxide is again O2, but now there is single negative charge. So try to understand the difference between these three types of oxides, because what element you have chosen from, that is group 1, depending on that different types of oxides will be produced when they are reacting with oxygen. Now look at these reactions. 4 lithium with 1 oxygen, it is forming Li2O. Now you can call it simply oxide or monoxide. Normally we call it oxide because by default when you are saying oxide, it is basically monoxide. Look at the formula, it is Li2O, because when it is monoxide, there is basically 2 negative charge, and 2 negative charge, if you balance, there should be 2 lithium plus. So that is why the formula is Li2O. Next element, when sodium is reacting with O2, now it is 2:1, 2 moles of sodium, 1 mole of O2, it is forming Na2O2, which is sodium peroxide. Now Na2O2, there is 2 negative charge, so you have to place 2 Na plus. You can also say it is as if derivative of hydrogen peroxide. In hydrogen peroxide we have HOOH, and now as if you are replacing the 2H plus with 2 Na plus. Okay, then the So these are the two elements, first two elements, lithium and sodium. After sodium, we have potassium, we have rubidium, we have cesium. And now we are representing the equation with capital M, because this equation is true for all these three elements. Okay, so this is the general equation for all these three. Now look at the formula. It is MO2. That means it can be, you can write it as KO2, or you can write it as RbO2. So why the formula is like this? It is because there is a single negative charge. So you just need one K plus to balance this negative charge. So look at this formula. It is, if I am writing in terms of M, it is M2O, this is M2O2, and this is MO2. So from the formula itself, you can understand whether it is superoxide, peroxide, or monoxide. Now these oxides, their nature is, they are basic in nature. And as they are basic in nature, when they are reacting with water, they form hydroxides. Okay. So how they form hydroxide, we'll also see that later. And right now we will see, because this discussion is simply, we are focusing how it is reacting with O2. We are not focusing that how the oxides are now reacting with water. That we will see separately. Now we are simply discussing how the alkali metals are reacting with O2 first and then N2. So O2 is done. Now come to nitrogen. Now when it is, we are talking about nitrogen, only lithium reacts with nitrogen, not other elements. And you there is proper logic also behind it, because O2 and N2, if you simply compare, obviously oxygen is more reactive than nitrogen, because in nitrogen there are basically three double bonds. Sorry, there is basically a triple bond present between two nitrogen atoms. And if you want nitrogen to take part in reaction, obviously these bonds should be broken. So this is energy requiring process. So the reaction is not so, it cannot take place so easily. And only lithium is reacting with nitrogen, because now if you are thinking that why it is behaving differently from the other alkali metals, there is also reason behind it. It is observed in general that when we study group chemistry, that is group 1, group 2, then group 3, 4, sorry, not 3, 4, group 1, 2 in S block, and then in P block there is 13, 14, 17 up to 18. So when we study this, you will see that always the first member of each group, its behavior compared to the other members of its group, it is different. So here also the same logic, and why it is so, we will come to that point also. But here we are having this information that lithium reacts only with nitrogen, not other alkali metals. And what it forms nitrite. One more information is that in this respect means when we are talking about reaction with nitrogen, lithium is more similar to group 2 metals. Now it is true that we not even started group 2, that we will see later after finishing group 1. But just remember this point, that lithium, its behavior, there is some similarity with group 2 metals, and it means that group 2 metals also, when they are reacting with nitrogen, they form this type of nitrite. What is nitrite? Nitrite is nitrogen containing 3 negative charge. 3 negative charge. You can also write it in 3 negative. Now to balance this 3 negative charge, 3 positive charge required. So that is why the formula is Li3N. So this is a balanced equation for the reaction between lithium and nitrogen. So reaction with air. After reaction with air, next we will see how it reacts with water. Alkali metals, when they react with water, that is actually very vigorous reaction. And as you are moving down the group, this vigorous character, that will even increase. So what they forms in, if we consider the general equation, it is 2M, where M is the alkali metal, 2H2O, it is forming 2MOH. OH means the hydroxide. So if it is sodium, it is NaOH. If it is lithium, it is LiOH. But for each cases, there is hydrogen liberation. The rate of the reaction of water with alkali metals increases with increasing atomic weight of the metal, which is another way of saying that down the group reactivity increasing. These reactions are highly exothermic. So that is why I'm saying that it is very vigorous reaction. So a lot of energy will be released, and that is why it is highly exothermic. Not just water, though here the discussion, the heading is reaction with water, but for extra information, remember that they also react with compounds where there is active hydrogen present. Now, when we are saying active hydrogen, it is basically these compounds. It may be alcohol, that is generally we write it like this, where this H is active hydrogen. Then you can consider alkyne. Alkyne is organic compounds. This is a general way you can represent it. So both sides we have some alkyl group, or it may be hydrogen also. But important point is this active hydrogen, this is applicable. Basically, I shouldn't write this formula. I should write at least one hydrogen. So this hydrogen which is directly attached to this triply bonded carbon, that hydrogen is active hydrogen. If R is also H, then there are two active hydrogen. So this is alkynes, hydrogen attached to sp hybridized carbon. Then gaseous ammonia, where also active hydrogen present. Now these compounds when react with alkali metals, see what is happening. We have taken sodium here, it is reacting with two molecules of ethyl alcohol, C2H5OH or ETOH. It is forming, see what it is forming. This H is now replaced with sodium, and now the formula is sodium ethoxide. It can also be written like this, ETO negative Na plus, or sometimes it is written like this. Mostly it is written like this, NaOH, which means sodium ethoxide, and hydrogen is removed. And if you take acetylene, that is the simplest alkyne, then these hydrogens now replaced by sodium. So what you are getting, see, Na2C2, and hydrogen is liberated. So there is some similarity with the equation when they are reacting with water. So that is why this is also important information under this heading, reaction with water. Reaction with hydrogen. All alkali metals can react with hydrogen. Look at the temperature, it is around 673 Kelvin. Only exception for lithium, for which you need more temperature. And they form ionic hydride. Now, what is hydride? Hydride means hydrogen atom carrying negative charge. When hydrogen carries positive charge, we call it proton. But when it is carrying negative charge, we call it hydride. So negative charge means when with this hydride there will be alkali metal, the formula should be MH, M plus H minus. Reactivity of alkali metals with hydrogen decreases from Li to Cs. Now this is something unusual. In the previous slide, remember, general information we have seen here, this point, that reactivity of alkali metals normally increases from lithium to cesium, and that is because of this resin IE. But remember, this is generally you can say, because most of the cases that is the observation. But there may be exception also, because some other factors are now playing the role. So what factors are playing the role? First, see, this is the general equation where M is any alkali metal. But when this M is lithium, the reaction can happen easily. But as you are moving towards cesium, the reaction becomes slow. Now, hydride, this is not very large ion, right? It is the anion is not very large if you compare with other ions. Now, as it is small, its binding with lithium plus will be better compared to cesium plus, which is there is a size is very large, right? So this is the reason there is a proper packing. So this is the reason, though ionization energy increasing, decreasing down the group, but here are some other factors around. So reactivity of alkali metals with hydrogen, it is opposite, it is decreasing down the group. So lithium can react better with H2 compared to cesium. So we have seen reaction with water, with hydrogen, with oxygen, with nitrogen. Now the very important, with halogens, how it behaves. So reaction between halogens and alkali metals. This is very, very important because halogens, they are group 17, and these elements are the most electronegative elements in the whole periodic table. And alkali metals, they are the most electropositive. So something very positive, something very negative. Obviously, the reaction that now we will see and the corresponding products, they will be ionic in nature. Fine. So because you have one partner which is highly electronegative, another partner which is highly electropositive. So electronegativity difference is very high. So ionic bond will be formed. So they form ionic halide. This is the general formula. M is any alkali metal, X is any halogen. Increases down the group because of decrease in corresponding I. Now this logic is now applicable. So this is the general equation. X is FCl, Br or I. All metal halides are ionic crystals. As I have said, the reason is electronegativity difference between M and X. This is very, very high. But some exceptions you have to keep in mind because exception related problems are very common. However, LiX, somewhat covalent. Now when I am saying LiX, it may be LiF, LiCl, Br or I. Now why it is so? That anion you are changing, but when lithium is fixed, covalent nature is compared to other alkali metals, it is high. The reason is if you consider Li plus and then other metals like Na plus or Rb plus, this is the smallest. So as it is smallest, but all are carrying same charge, it is +1 for all, but it is smallest. That means its size is smallest, volume is also smallest. Now charge by volume ratio is charge density. Charge density is very high, and when charge density is very high of the cation in any ionic compound, then there is some covalent character generated, and that is according to Fezan's rule, which is discussed in detail in chemical bonding chapter. Now LiX, whether X is FCl, Bri, you can say they are somewhat covalent. And which is maximum covalent? Lithium iodide being the most covalent among LiCl, LiF, LiBr, Li. So among all the LiX, this is the most covalent. Why? Now we know lithium plus, that is fixed. We are just changing the anion, and when we have reached I minus, then it is maximum, its size is max compared to other halogen. That means volume is also very high. Now when the anion is very large, it becomes highly polarizable. So in any ionic compound, how much covalent character you can expect, that is according to Fezan's rule. And Fezan's rule is saying when the anion is highly polarizable because of this type of a large volume, then there is covalent character generated. And obviously if the cation is having very high charge density, then also covalent character generated. Because when Li plus, that is when cation is having very high charge density, its polarizing power, that is to polarize the anion, that is actually polarizing power, that is very high for lithium plus, and I minus, that is also very large in size, so it becomes maximum polarizable. So it is true that in general LiX is somewhat covalent compared to other MX, but among LiX, Li is the most covalent. Okay, so these are important information. The next reaction we will see is reducing character. Reducing character means what? They are capable to reduce other species. That means alkali metals, they can feed electron to other species, that is other species are accepting electron from these alkali metals. So they can lose their valence electron readily, that we know. What is the reason? That we know. And they can act as good reducing agent. Now, okay, it's fine that they are having good reducing agent, but among all the alkali metals, how we will know which one is most reducing, having most reducing character? To answer that question, Electrode potential values. Basically, it is reduction potential. When nothing is mentioned, simply consider it as reduction potential. That is the general convention. So these reduction potential values of these metals, that helps us to decide which one is most reducing, which one is least reducing. So here it is mentioned sodium is least reducing, lithium is most reducing. But why? Look at these values. So for all these reactions, that is basically it is donating, they are donating electron. So for all these reactions, if you look at the reduction potential values, in all cases it is negative. Now when there is negative, it means reducing character is good, and more positive it becomes, reducing capacity is very less. Now which one is most negative? See, this is most negative, so that is why it is most reducing. And which one is least negative? So that is the reason least reducing. Okay, so it is not gradual, there is nothing smooth trend. After lithium, these three are almost same, and then the lowest is for sodium. Reaction with carbon. Lithium directly reacts with carbon and they form ionic compound lithium carbide. But for other metals, there is no direct reaction with carbon. So again, you are seeing one property of lithium where it is behaving differently. That is, its behavior is not similar as the other metals, because other metals are not reacting, but it is reacting. Fine. So when it is reacting with carbon, it is forming carbonate. Now the formula is Li2C2. Li2 means what? Total positive charge is 2 plus, and that means C2, overall C2 must carry 2 negative charge like this. So it is basically triple bond between 2 carbon, and both sides there is a negative charge. So 2 carbon carrying 2 negative charge. This is formula of lithium carbide. Now the very important, this is very unique behavior, because when you will see as we proceed through this chapter and also the p block elements, the next chapter, there you will see mostly when we discuss chemical properties of any particular group, whether it is p block groups or s block, we mostly there are some common elements fixed, that is O2, nitrogen, water. So these are common, and halogens, X. But you will hardly find that how they react with ammonia, that is especially liquid ammonia. But now this reaction, this is very unique for alkali metals and also for alkaline earth metals. So here some important informations we will get, some interesting behavior. So when we take liquid ammonia, not gaseous, liquid ammonia, then alkali metal can be dissolved in it. And after this process, we get a deep blue colored solution. Now these deep blue colored solutions, it is observed that they are conducting in nature. Now when there is conducting nature, there must be some free electron present. So what is happening here? Alkali metal, they can readily lose its valence electron, that we know. So when these electrons are removed from alkali metal in ammonia solution, what happens? Now this electron is surrounded by many ammonia molecules. Now as you are dissolving in liquid ammonia, so liquid ammonia is basically here the solvent. Now as this electron is surrounded by ammonia molecules, so you can consider it is solvated electrons, because surrounding electron there is ammonia molecules. And here it will be, you can consider this picture. Suppose you are dissolving sodium metal in liquid ammonia. So sodium metal, it will lose electron, and these electrons will be surrounded by ammonia molecules. So see here N is mentioned as if N number of ammonia molecules are surrounding it. Now look at this molecule. Here this part is N. See if I am drawing it here. It is drawn in this box like this. So it is actually M, H, H, H. Now N and H, which one is electropositive? H is electropositive. So that is why all these H, they are facing the electron. They are facing the electron because it is negative. But when it is Na plus, then also ammonia, several ammonia molecules are surrounding it. But now the nitrogen is facing Na plus, because nitrogen, that is the negative, there will be partial negative charge in nitrogen. So that is why they are facing Na plus. So here also several ammonia molecules are surrounding Na plus, and you can call it as if it is ammoniated Na plus, and here it is ammoniated electron, or in general you can say solvated electron. But as the solvent is ammonia, so I am saying ammoniated electrons. So the equation you can represent like this. Both the cations and electrons now ammoniated or solvated, so that you can get ammoniated cation and ammoniated electron, this one. Now the equation will be M, that is any alkali metal, and there is X plus Y number of ammonia molecules. X and Y, it may be very large number. Now M, it has already lost the electron, so as if it is surrounded by X number of ammonia, and the overall charge is mentioned outside this third bracket. This whole term, it is within third bracket. Outside the third bracket there is positive charge, and this single electron which has we are getting from this sodium after loss of electron, this electron is removed from sodium atom, and now it is surrounded by Y number of ammonia molecules, and the negative charge is mentioned outside this third bracket. So this is this ammoniated electron. Now this solution, it is blue in color, and there is also some specific characteristic of this solution, and study it very carefully because you will get question regarding it. So see how the solution looks. It looks like this. It is blue color. Now the important characteristic, it is paramagnetic. First important characteristic, it is blue in color. Second, it is paramagnetic. Paramagnetic because of this unpaired electron. In the previous slide you have seen unpaired electron surrounded by ammonia molecule, that is ammoniated electron. It is not paired, it is single, unpaired. So that is why it is showing paramagnetic property. And these ammoniated electrons, they absorb energy in the visible region of light, and the wavelength is such that you ultimately see the blue color. So what is the reason behind this blue color? It is because of the second statement. That is the reason. Now there is some similarity. Remember, when metal reacts with water, what happens? We get MOH and we get hydrogen. If you balance it, it will be 2. This is 2 and 1 H2. Now here what is happening? Metal reaction with water. The salt that you are getting hydroxide, there is actually hydroxide ion present. But when metal is reacting with ammonia, just like water, if you remove one H from H2, you get HO minus, just like that. When you remove one H from ammonia, you get NH2 minus. This is known as amide ion. So just and is in their reaction, that is the reaction with water. Alkali metals behave similarly. They also react with liquid ammonia and they produce hydrogen gas. So here also hydrogen gas is produced when they have reacted with water, and now they are reacting with ammonia. Here also you are getting hydrogen gas, and this hydrogen gas, it is basically half hydrogen. If you put 2 M and 2 NH3, then it will be 1. That is the coefficient will be from half to 1. So hydrogen is liberated, M plus and NH2 minus. So these two together, here in the bracket AM is written. AM means ammoniated. Fine. So this is M plus. Sorry, this is not ammoniated. M plus is ammoniated. So this M plus and NH2, if you write it together, it will be this metal amide. For example, if I write sodium, the formula will be NaNH2. For potassium, it is KNH2. So this is sodium amide. So you can find some similarity with MOH. So OH from water you are getting by removing one H. NH2 you are getting from ammonia by removing one H. Similar type of behavior. One more important point. So up to this point it is okay. But suppose you are increasing the concentration of the metal above 3 molarity. Now the color changes to, see, there is a drastic color change. Now it is becoming metallic bronze or simply gold color, and the system now diamagnetic. Initially when it is blue it is paramagnetic, but now when it is bronze color it is diamagnetic, because now as the concentration of the metal we have increased, the electrons, they are coming close to each other, they are pairing with each other. So it is no longer unpaired electron. So it looks like this. That is the bronze color, or you can say gold color. So here important information, it is blue, paramagnetic. Reason for paramagnetic, there is absorption of energy by this ammoniated electron in the visible region. Next important information, we get MnH2 type of salt. Just like it reacts with water, we get MOH. Next important information, if you increase the concentration beyond a particular level, now the color is changing from blue to bronze. It is paramagnetic, but it is diamagnetic. So these are the some important unique features for alkali metals when they are reacting with liquid ammonia. Now some questions. Which one among the following metals weakest reducing agent? Remember one table we have seen based on reduction potential. So here we have seen the weakest one, that is clear from this one. So sodium should be the correct option. Okay, RB. Option 2. Next question is, identify the incorrect statement from the following. So we have total 4 statements. There will be one wrong statement. The first statement, oxidation number of potassium in KO2, it is saying +4. See, we know that oxidation state of alkali metals, only possible oxidation state is +1. There is no other oxidation state possible. This information is enough to answer that this is actually false statement. Even if you do not know that KO2 is actually superoxide, it is not normal oxide, because if you consider it as normal oxide, per oxygen there is 2 negative charge. So for 2 oxygen atom there will be total 4 negative charge. So if you want to balance this 4 negative charge, as if potassium is having oxidation state +4, but how it can have potassium oxidation state +4? Because the only oxidation state possible for any alkali metal is always +1. So even if you do not know it is superoxide, then also you can easily understand that it is wrong statement. So we have already obtained our answer, but the next question is why the other 3 options are true. That also you have to check. Next statement is saying that ionization enthalpy of alkali metals decreases from top to bottom in the group. Now that is, we have discussed several times. It is true. Lithium is the strongest reducing agent, which is clear from this table itself. So this is also true. Alkali metals react with water to form hydroxide. So this equation we have just seen. If you take sodium, it will be 2NaOH. So they are forming hydroxide. So this is also true. So here wrong statement is, that is the incorrect statement is the first one. The metal that forms nitrite by reacting directly with nitrogen. So here the 4 options all are basically alkali metals. Now alkali metals, when they react with air, in air there is O2 and there is N2. Now reaction with O2 in detail we have seen, oxide, monoxide, superoxide, all these. This is a form. But reaction with nitrogen, when we consider, there is one particular metal, alkali metal, which reacts, and that is lithium. So this should be the correct option. Only lithium reacts with nitrogen and it forms lithium nitrite, Li3N. So here nitrite means nitrogen carrying 3 negative charge. So to balance 3 negative charge, we need 3 potassium. If you simply dissociate it just for your clear understanding, it is basically 3Li plus N3 negative. Okay, nitrite. Nitrite means one single nitrogen carrying 3 negative charge. But rest of the elements, they are not reacting with nitrogen directly. There are some specific conditions required, not direct reaction. Next question is, all these elements, that is lithium, sodium, potassium, they are from group 1. Now one information I would like to mention that here we are discussing group 1. So obviously the questions will be based on group 1 elements. But remember, when we will actually solve question in examination hall, the question you may get, it may be related to any group. Now from which group the question is given, that you have to understand, right? So here the elements that you are seeing, lithium, sodium, potassium, you have to recognize that they are from group 1. Once you know it is from group 1, then only you will be able to answer the question. Okay. So combustion of lithium, sodium, potassium, it is saying in a different way, it is using some different word. Combustion. Combustion is something a reaction with oxygen. So it is not directly saying that reaction with oxygen. It is simply saying in another way, combustion of lithium, sodium, potassium in excess of air. So it is basically reaction of metals with oxygen. Now when this metal is lithium, now we will get normal oxide, which is having formula M2O, and only one M2 is there, which is for lithium. Then if it is sodium, we get peroxide, which is Na2O2, and if it is potassium and the other elements, cesium, Rb, then the formula is MO2, which is the superoxide. So for lithium, it is Li2O, which is present in option 2 and 4. Then Na2O2, which is present in 1 to 4, but 2 and 4, it is already cancelled. Na2O2 and KO2. So this is not correct. Option 2 should be the correct option. So these are the equations. Once more, you can see here. So same equations we have already discussed when in the slide reaction with air. Okay. The first chemical property is the first slide. So correct answer is option 2. So this question is related to liquid ammonia. Assertion statement, reason statement, and as you know, the format of assertion reason type of question. So first read the assertion statement. It is saying that metallic sodium dissolves in liquid ammonia, it gives blue colored solution, which is paramagnetic. Now this is absolutely true. The first solution we get blue, and it is also paramagnetic in nature. Now paramagnetic is because of this unpaired electron. Now second statement is saying in the reason that the deep blue solution, what is its reason? It is saying that it is because of formation of amide. Remember, amide general formula is MnH2, that is M plus NH2 minus. So this NH2 is coming from ammonia by loss of one hydrogen. It is formed, that is true, but is this the reason for the blue solution? No. The blue solution is because of the absorption of this single unpaired electron in the visible region. Okay, so this cannot be the correct reason for the assertion. Deep blue solution, it is because of some other reason, not because of amide formation. So A is obviously correct, but the other statement is not correct. Okay, A is true, R is false. The reason is different. Uses of alkali metals. So after finishing chemical properties, some uses we will see. So here we have the first element, lithium. Lithium metal is used to make some useful alloys. So when we are talking about alloys, there will be combination of two metals and they form a completely different species. So for example, it can make alloy with lead and it is called white metal, which is used in bearings for motor engines. It also forms alloys with alumina to make aircraft parts. So suppose you may get question that for aircraft parts making, the alloy, which alloy of lithium is used? Is it lithium Pb alloy, lithium aluminium alloy, or lithium Mg alloy? The answer is lithium aluminium alloy. And when the alloy is with magnesium, it is used for armor plate preparation. It is used in thermonuclear reactions, also in making electrochemical cells, and lithium carbonate compound, that is the carbonate salt of lithium, Li2CO3. The formula is so because carbonate is carrying 2 negative charge, so we need 2 lithium. Now lithium carbonate, it is used as medicine. Sodium. Sodium is used to make sodium Pb alloy, lead, just like lithium, and also to make Pb alloy. And now this alloy is used to make PbEt4, PbMe4. So it is that is metal with some hydrocarbon part, right? So this is called organolate. Organo, the term is coming from carbon hydrogen combination, that is ethyl or methyl group, which is organic chemistry. We use the term ethyl or methyl. So it is, that is why we are calling it organolate. These compounds are not used nowadays, but earlier it is used as anti-knock additive to petrol. So they are added to fuel, anti-knock additives. Details we don't need to know, just remember these are added to fuel for its maximum efficiency. But nowadays it is not used, lead-free petrol is used. Sodium is also used in the production of sodium vapor lamp, and the liquid sodium is used for heat transfer in nuclear power station. What about potassium? KCl is used as fertilizer. KOH is used in the manufacturing of soft soap. It is a very good absorbent for CO2. Now this use of potassium, basically KOH is used, and it should not be that K is directly used, and the potassium hydroxide is actually used. And to make potassium hydroxide, obviously you need potassium. It is used for excellent absorption of carbon dioxide gas, and this use of KOH you will also see several times in other chapters. Potassium has a vital role in biological systems. Now, sodium and potassium, these two alkali metals, they are having some important role in biological system that will be discussed separately, but in the users part also you have to consider it. Okay? Cesium is used in devising photoelectric cells. So these are some uses of alkali metals, as we still have some time left. So once we have finished chemical properties, and in chemical properties, remember we have seen that it is reacting with oxygen, it is forming oxide. Then oxides, when reacting with water, it is forming hydroxide. So different types of compounds are formed. Then remember, when it reacts with halogen, it forms halide. For example, sodium chloride, potassium chloride, potassium bromide. So these are formed. So these are halides of alkali metals. So in chemical properties part, we have seen what are the type of compounds we get from alkali metals when it is reacting with different other elements. Now, once we know what type of compounds are formed, that is, we have seen how oxides are formed, how hydroxides are formed, how halides are formed. Once we have already discussed it, now what we'll do, individually we will try to see the characteristics of these compounds, that is characteristic of oxides of alkali metals, characteristic of hydroxides of alkali metals, one by one. After this we will also see halides. Okay, so the first statement, it is saying that on combustion in excess of air, we have already seen that lithium forms Li2O. Some amount of Li2O2 may be there, but that is insignificant. Sodium mainly forms Na2O2, and these three forms superoxide, formula MO2. So this information we have already seen in the chemical properties part. Now this oxide, in this table you can see monoxide, this is the formula, peroxide, this is superoxide. And all this oxide, what type of anion is involved, that is also clearly mentioned. with the oxidation state. So this information up to this we already know it. And these oxides, there we have also mentioned that these are basic, and when they react with water, they form hydroxide. Now you can see these reactions. So the oxides, how they are formed from oxygen, that you already know. But these oxides when react with water, now what is formed? So in each case, there is formation of MOH. Okay, but this is a common part. But what is the uncommon part? Uncommon part is in Li2O you are getting only MOH. In Na2O2 you are also getting H2O2. And in the last reaction, that is in case of these three elements, you are not just getting MOH, you are also getting H2O2 and O2. Okay, so the byproducts are different. Here we do not have any byproducts. So this is very important information. Common point MOH formation fine, but what are the different observations, that also you have to, that factor you have to take care of. So we will not extend it anymore. So this much information related to oxide, we'll finish it here. Next day we will see what is the characteristic of these oxides and hydroxides. Okay. So we are ending the session here. Thank you for listening.